Okay, continuing the discussion of the symmetric slab in Chapter 4. So we just saw the picture of the symmetric slab where the cladding on both sides of the core has the same index N2. N1, the index of the core, is larger, and so here's our index profile. Define TE and TM polarizations. And now what I want to do is I want to try to convince you that I'll draw the picture here and try to convince you that not just any angle. Okay, so we've got these rays which sort of bounce back and forth inside this waveguide. As long as their angle of incidence on the core cladding boundary is larger than the critical angle, these rays should bounce around forever. Well, it will not happen for any incident angle. Only certain incident angles will bounce forever. And the reason is that when this ray bounces forever, you can think of it as a ray, but you can also more properly think of it as sort of a wave front, which is simultaneously going at two different angles through this waveguide. And the condition for, and these wavefronts all have to interfere with each other constructively upon traversing a complete cycle. So for example, as I go from here through one complete cycle of the bounce, okay, this is one cycle. In order for this ray to really propagate forever inside this waveguide, we've got to have a phase change, delta phi, which is an integer multiple of 2 pi. This is the standard condition for constructive interference. If it were an odd integer multiple of pi, then we'd have exact destructive interference. It turns out is any time the phase change is not exactly equal to an integer multiple of 2 pi, meaning that we have complete constructive interference over one cycle, then the destructive interference over many cycles will cause rapid attenuation of that ray. And so only rays which can satisfy this condition will propagate. And so the phase angle advance includes two terms. It includes both the path length and phase changes on reflections. If we look back at the equations for the reflection of light, then we can analyze them and see that we'll get a 90-degree phase shift as light is reflected internally. And I guess I can't find the pictures of the reflection coefficients. In any case, the analysis is complicated, and we're going to just pretty much write down the result. The one part that is easy to understand, though, is the phase change due to path length. As a wave goes a certain distance, its phase changes by, let's call that the z direction, the direction of propagation. The phase change is an integer multiple of 2 pi as z changes by the wavelength. Okay, so as we go in the z direction by one wavelength, our phase angle has incremented by 2 pi, and that can be seen by recalling the E of z and t. The electric field is going to be some amplitude times the sine of k z minus omega t, where k is 2 pi over lambda. Okay, so we have this term kz, okay, and as z goes from 0 to 2 pi, kz advances, let's see, as z goes from 0 to lambda, kz advances from 0 to 2 pi. So as z is equal to 0, kz is equal to 0, and when z is equal to lambda, kz is equal to 2 pi. So you can see that advancing in the z direction by a distance of lambda has advanced kz, which is the phase of this sine wave, by 2 pi. Anything inside here is the phase. So the phase advances in space and time. In any case, the analysis is complicated, and we won't go through it here, but this is called the phase matching condition. Okay, and as I say, the phase advance includes not only the advance through this distance, but also potentially 90-degree phase shifts or 180-degree phase shifts, one or the other, upon these reflections. And the result of the detailed analysis is that well, we have two results for TE and for TM. For TE we have the tangent of HD over 2, and for TM we have the tangent of HD over 2 plus pi over 2, and this is equal to, can I fit it here? It's equal to the square root of n1 squared sine theta 1 squared minus n2 squared all over n1 cosine theta. Okay, so this is the phase matching condition. Okay, kind of a complicated thing. What we're going to do, oh, and in this equation, H is equal to K cosine theta, which in the material is 2 pi n1 over lambda. This is inside the core, cosine theta. Okay, so K is inside the material, and that's why we've got an n1 here. Okay. Anytime we have the tangent of something equals something else, then we have the possibility of multiple solutions. And in fact, if we go ahead and say, okay, we're considering this slab with these indices, n1 and n2, we're going to fix them, and we're also going to go ahead and consider this particular ray with its incident angle theta, we're going to fix that. That fixes the entire right-hand side here. Okay, so this whole right-hand side is a constant. And any time we have the tangent function equals a constant, then we have the possibility of multiple solutions. So we have our tangent function sort of looking like this. These asymptotes, lots of vertical asymptotes. And anytime we set the tangent function, here's x, here's tangent of x. Anytime we set the tangent of x equal to some constant, we get a lot of x values for which that holds. Okay? And so there are multiple solutions to this thing. And this periodicity here is in pi. Okay, so as x advances by pi, we get another solution to the equation. Okay? And I think I'll stop here and move on to the next video for the next slide.